welcome back to Advent of Code 2024, day 20. Welcome in, Umaro and TJ. Alright, I don't know what people thought of this one. Short day today? Okay, well. What was yesterday again? Yesterday was short as well, wasn't it? Yeah, that was pretty short. Okay. Race condition. Wonder what the picture is going to be. Oh, what this? It seems it's just like in line with the theme, so it's just showing little mini pics of all the past things that appeared in previous years. I feel like this one here is Falling Sand, because that was a very popular that was a very interesting one. He was simulating falling sand and how it moves and how it spreads out. Similar to like in Minecraft, when sand falls on sand, it like rolls to the side. You had to do the same thing. All the others, I can barely even see what they are. Christmas tree there. More like it's just a 10. Oh yeah. I mean, that's the outer layer is the 10, definitely. I'm just talking about like the inner pictures. Yes, it is the 10th anniversary. Guess that's why we're having like a clip show anyway. The historians are quite pixelated again. This time a massive black building looms over you. You're right outside the CPU. Okay, don't really remember this one. While the historians get to work, a nearby program sees that you're idle and challenges you to a race. Apparently, you've arrived just in time for the frequently held Race Condition Festival. The race takes place on a particularly long and twisting code path. Programs compete to see who can finish in the fewest picoseconds. The winner even gets their very own mutex. It's a snippet of code that handles like locking. They hand you a map of the racetrack. Alright, so this is going to be similar to the reuse the code from the reindeer, I suppose. Yeah. When a program runs through the racetrack, it starts at the start, then it's allowed to move up, down, left, or right. Each such move takes 1 picosecond. The goal is to reach the end position as quickly as possible. Because there's only a single path from the start to the end, and the programs all go the same speed, the races used to be pretty boring. To make things more interesting, they introduced a new rule to the races. Programs are allowed to cheat. The rules for cheating are very strict. Exactly once during a race, a program may disable collision for up to 2 picoseconds. This allows the program to pass through walls as if they're a regular track. At the end of the cheat, the program must be back on normal track again, otherwise it will receive a segmentation fault and get disqualified. Alright. Fine. Each cheat has a distinct start position. The position blah 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 blah. Each cheat has a distinct start position, the position where the cheat is activated just before the first move that is allowed to go through walls. And the end position. Cheats are uniquely identified by their start position and end position. In this example, the total number of cheats are as follows. You aren't sure what the conditions of the racetrack will be like, So to give yourself as many options as possible, you will need a list of the best cheats. How many cheats would save you at least 100 picoseconds? So, fine. I guess we want to start by just computing the distance of every node to the end. And then when we place a cheat, so I've noticed that we don't have a situation where you can move diagonally between two walls. That could come up though. It would fit the description. It would count as moving two spaces, so I guess we should account for it. Fine, so if we knew the distance of every node to the end, then adding a cheat would tell us and if we knew the distance from the start to every node, so two separate iterations of BFS essentially, then every time we pick a cheat, we would be able to compute the distance using that cheat would take by running this from the start to the first part of the cheat, and then running from the second part of the cheat to the end, adding those two together, right? Plus 1. It takes 1 picosecond, is it? 2 picoseconds. For up to 2 picoseconds. Alright then. Okay. So, okay, once we've got the shortest paths to the start or the shortest paths to the end, then yeah, we just loop basically over every possible cheat, I guess. It is a tree, right? So it's like... It's not a tree, but there is one unique... Okay, let's do it. Yeah, it looks like we never really have a diagonal move, but I'm not going to make any assumptions. So... So let's reuse our code from, what was it, 18? $17, $16, $19? I don't remember. Where are we reading the, yeah, it was 16. Oh yeah, this Dijkstra method here. Okay. So... But we want roughly the same pos classes as you used a couple of days ago. Okay, this one. Well, I'll just use this one because we don't need to check for inbounds. The map is contained by the outer wall. Alright, so we've got pos class. Hello, Galvabar. Just got started on this problem. Alright, we could reuse a lot of code here. So we've got add, subtract, quality, hash. Probably won't need this. We're not using a priority queue. And then we got get neighbors. Alright, and then we've got grid class. Oh, where did I do the grid class? Here, yeah. Alright, so grid is that. It's got a height, it's got a width, it's got a string method, it's got a get, that's very useful. We don't really need to check in bounds. Oh, we'll just include it anyway. No, just take out all the stuff. It just reduces the risk of error by not using methods we don't really need. We'll just go with that and that. Okay. Alright, and then when we populate a grid, we basically do this same thing like this. Text from row to row. If s in row, j equals row dot s, there's one s and one e. Alright. Print grid. Okay. Grid, print, start, end. Okay. Alright. So I think what we want is a BFS method. We don't have to keep writing this out every time. I think we just copy. When did I do BFS? I think it was 18. Yeah. Let's use this. But it's not a start to a goal. It's just from a start. Alright, so, and then we want okay, so we take Q, start, and we want the dist, while Q, okay, so we don't do a neighbor check, a goal check, take that out. Alright, so we don't do an obstacles, but we do say if grid.get neighbor equals hash, that's an obstacle. Alright, if neighbor and dist continue. Alright, that is BFS, and we return this dist map. Alright, Alright, so the point of this is it will give us... It will exhaust the entire map, every reachable node, and give us the distance from... distance to each of these nodes. The keys are the nodes, the values are the distances. Okay. So... start equals grid.bfs start from end. When you can say to end, just say from end equals grid.bfs end. Let's just see what these look like. Also, shortest path equals from start to the end, which we also need that value. Okay. 9452 is the shortest path. Okay, let's just check that that matches the other way around. From end start. Okay, good sign. All right. So we have a table of values now. We want we only want cheats that go through walls, because cheats that don't go through walls aren't actually going to achieve anything, are they? Not that it would matter, it's a simple lookup from the table. Alright, we'll just include all cheats. Alright, so we're going to go... we do need inbounds check, because the cheat can take us through the wall. I forgot about that. Did I include that? No, I deleted it, didn't I? Okay. Alright, it's inbounds. Okay. Alright, so for cheats, okay, for I in range grid dot height grid dot height for j in range grid.width cheat start equals pos ij if grid dot get cheat start is a hash. Skip that one. So you start from an empty space. Okay. And then we say for neighbor in hang on. This actually matters. Does the cheat have to go through a wall? I just realized because we're counting. Well, a cheat that doesn't go through a wall wouldn't reduce the time anyway. Also, looking at their description, they only when they list, they say the total number of cheats are as follows, and they don't list any cheats that save 0 time. So they only count a cheat as something that saves time. Not that it matters, because at the end of the day, we only want to find cheats that save us at 100 picoseconds. But the definition of a cheat might matter for part 2, I don't know. Yeah, looking at the actual definition of cheat, it has to start on a space and end on a space up to 2 spaces away. But 1 space away, there's no point. So up to 2 spaces away, and it's allowed to pass through walls, but it doesn't have to. So that's the definition of a cheat, really. You can turn God mode on, no clip on for 2 seconds, regardless of where you choose to go. All right. So for neighbor in grid.get grid.verb. We don't want the grid method of getting neighbors. We want the pos, because we can go through walls. So yeah, neighbor in cheat start dot get neighbors. Let's say that's neighbor 1. For neighbor 2 in neighbor 1 dot get neighbors if, so that's basically up to 2 spaces away. It could be the same space, doesn't matter. If grid dot get neighbor 2 is an empty space, then this is a valid cheat by their definition. So including a lot of pointless cheats, but it doesn't matter because it's just an arithmetic operation we're doing. It's not going to waste that much time. Okay, so if cheat, then we want to see how much time is saved. If we're using this cheat. So the time saved will be path length equals, so it's going to be from start to cheat start. Let's rename these. Let's say that's neighbor, that's cheat end. Plus from and cheat end. So what are we trying to find? The number of cheats that save at least 100 picoseconds. Okay. So let's call them good cheats equals 0. If shortest path minus path length is greater or equal to 100, good cheats plus equal 1. Alright. In line 74 you have no, because continue means skip this one, go to the next iteration of the for loop. I could have written it as if it equals dot, and then this whole thing would be indented. But I do this to save on indentation where I can, so I thought cheat start must be a... No. Cheat start must be a space. Cheat end must be a space. The midpoint, neighbor, can be anything. So you're moving 2 spaces. Starting from a space, ending on a space. But you could define it differently. Like you could start from a wall. Well, that would be a bit messy. I wouldn't want to do it that way. Alright, let's try running it then. 1467. It's quite a lot. Okay. So there's this many that save 100 picoseconds. Sounds plausible. Nope, it's too high. Okay. Shortest path minus length, path length. Okay. Oh. That's interesting. I'm not doing an inbounds check. We could be going off the grid. But then what would happen if we go off the grid? Grid.get would be a none. So that's fine, but I should really handle this separately. So cheat start is inbounds, we know, because we forced it to be. Neighbor cheat end, it doesn't matter where neighbor is, neighbor could be anywhere. Cheat end could be out of bounds. If grid dot is, or just say if grid dot is in bounds cheat and that. I think we'll get the same result because it was basically doing a none check, but I'd prefer to make this explicit. 1, 4, 6, 7. Okay. Is this logic even correct? Oh! I see the problem. We forgot to add 2. The cheat itself costs 2. Okay. 1, 4, 6, 7. 1, 4, 5, 9. Alright. You don't just teleport. Correct. Okay. Okay, good. The program seemed perplexed by your list of cheats. Apparently the 2 picosecond cheating rule was deprecated several milliseconds ago. The latest version of the cheating rule permits a single cheat that instead lasts at most 20 picoseconds. Oh boy. Now, in addition to all the cheats that were possible in just 2 picoseconds, many more cheats are possible. This 6 picosecond cheat saves 76 picoseconds. This 6 picosecond cheat saves 76 picoseconds. Yeah, okay. Because this cheat has the same start and end positions as the one above, it's the same cheat. Yeah. Cheats don't need to use all 20 picoseconds. Cheats can last any amount of time, up to and including 20 picoseconds. So you would think we could just increase it to 20. So this bit here, okay, let's wrap this up as a method first. Then we'll think about whether it will actually run in time. Like 20 by 20. Okay. Let's see how we can code this. So we want to say define get num good cheats. So it's going to be Um, basically all of this. But we need a parameter. It's going to be max cheat length. Alright, so that I range for Jane cheat start. We do the same thing here. And then we don't do this. We've got to say so we want all the so it's a diamond shape, basically, the Hamming distance away by of radius 20. So we want to say for say k, it's just like a row, temp row variable for ik in range. So we go from like minus max cheat length to max cheat length plus 1. For j wait, so when you're that far away, what is jk is allowed to be? So jk at jk max, it's a jk max is so that when I is that jk, the max it's allowed to be is going to be max cheat, and there's probably cleaner ways of doing this, range, max cheat length minus abs of ik for jk in range minus jk max. So for example, if ik was max cheat length, then jk has to be 0. Okay. So the delta is going to be ik jk. All right, so we're saying that is the vector we can go away with this cheat. All right. And so what 20, so it's like 40 by it's gonna be like something like 20 by 20, isn't it? It's like 400 times 100 times 100. I think we can, this is gonna be in the millions, tens of millions maybe. I think it'll be okay. Then cheat end equals, or just say cheat end equals cheat start plus that. And then, so we don't need this. And then we just do this. If that place, that location is inbounds, and it's an empty space, then path length equals from start plus, and this is going to be absolute value of ik plus absolute value of jk, because that's how far we use the cheat. Ah. But we're not. Yeah, no, that's right. Okay. And then if shortest path minus path is greater equal to 100, good cheats plus equal 1. Alright, so if we rerun this now, hopefully we get the same result. Print good, do it. Print get good num cheats 2 max cheat length. So it's even going to try cheats of size 0 and try size 1, but they're not going to save time or anything, so they won't affect anything. None. Yeah, just comment this out. Because we didn't actually return anything. One, 4, 5, 9. Same answer. So we've got a method which works for part 1. So, big question on everyone's mind is 20. Right. I need some indicator to know how far it's actually getting. Oh, we're done. Huh. Alright, let's try it. I can't think of any obvious flaw here. If it worked for 2, then changing the number 2 to 20 shouldn't introduce an error, I don't think. Correct. That ran faster than I thought. I mean, it's like 20. It's a 20 by 20 diamond, so it's like 400 cheat end positions, so it's going to be like 400 times. Well, it's not. This is going to be more than that. It's 400. It's the No. That's about right. 400 times. This the number of cells in the grid, I guess. But let's say half that, because only half of them actually have spaces, so it's in the millions, I guess. That was a nice problem. I wasn't that part 2 wasn't that hard to generalize. Like, the only traps you could fall into really are Like, for example, you could... I'm guessing this would still work, but you could, instead of choosing a cheat start and a cheat end within range, you could just pick every two possible points on the map, check if their distance is at most 20. But that's basically the same thing, and that's actually not that much worse. So that's fine. Well, it is a bit worse actually, because yeah, no, because you are ranging over. It's actually like 100 to the power 4. Yeah, that'd be kind of bad. That'd be 100 times worse, basically. Or more than 100 times worse. Yeah, so maybe some people did that because, like that is one thing you might think of doing, like when they say distinct start position, distinct end position, just try all start positions and end positions. I think that would be too slow. You'll probably finish though, but it might take minutes or longer. Yeah, other than that, it wasn't that hard. I mean, the key trick here was to store all shortest paths, really. Not all shortest paths, just all shortest paths starting at S and starting at E. So that's significantly less. So you don't have to use, like, if you wanted all shortest paths in the entire grid, you could use, like, Boyd-Warshall's algorithm or something to get them all, which is cubic. But if we just need the ones from S and E, it's like linear or quadratic or something. How did you store all the paths? I didn't store any paths, I just stored the distances. So I stored a distance table from S to every cell on the grid, and I stored a distance table from E to every cell on the grid. So any cheat would be, if cheat goes from A to B, then the whole distance is S to A, which we have in our table, then A to B, which is the cheat length, and then B to E, which is the reverse of the E to B. And BFS does that, right? Yeah. Like one iteration of BFS from S would get you the distance to every cell, and then do another iteration from E, and that will get you the iteration to the other cell. So it's like a... there's actually a pathfinding algorithm which is similar to that, where you actually run a BFS from both the start and the end simultaneously and concurrently, and see where they meet. There's some reasons that there's some practical advantages of doing it that way, but I have never coded an algorithm doing that. I guess it's for graphs with a really high branching factor, but you happen to know that the start is close to the end. That actually comes up in biology and stuff like that, where you like similarity between cells. You know that things are close together, but when you go through the breadth of the graph, the breadth is really, really huge. In which case, if you want to find the distance between two entities, you might want to do a simultaneous search from the start and the end and see where they meet. That cuts down your branching factor by quite a bit. Yeah, I think that's one of the applications of it. But that's nothing to do with this. Okay, I'm glad that didn't take long because I didn't have long. I'm quite tired. I had a flight today and I didn't even sleep beforehand because I can never sleep before early morning flights. So, get the rest of my evening back. I was still working on day 19 this morning. Some people had cool results, such as using a simple regex made of the towels. Ooh, interesting. Did it run in time? I don't think regex is powerful enough to. Maybe for part one. Well, even what? I'm not sure exactly what they're doing with the regex, but I guess. Um, yeah. I wouldn't think regex would be powerful enough to do that. There's like mathematical laws on things that regex can't do. Okay, that's cool. You just use tau one or tau. Oh, I see. Yeah, but then the search space would be the same, I guess. Yeah, I guess that's sort of. Yeah, I mean, you're not exiting early, but you don't have to. And it's not going to be using any caching. So I guess it'll work. It'll just be really slow because you're not using caching, but it is functionally equivalent to to doing dynamic programming the inefficient way. All right. How many more grids are we going to get? All right, so 16 was a hard one, it seems. Was it? What was this one again? This wasn't that hard. It doesn't seem like many people have. Um. Oh, wait, no. If the silver stars is fewer than that, then that means people found 17 harder than 16. Oh yeah, 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 definitely. This was the end code. Did you get all stars so far and missed out on some? Yes, I have all stars so far. I have all stars ever in Advent of Code so far. uh, Across all events. Let's see if I can keep it up. Oh no, I don't have 2021. I forgot. I don't have all stars ever. I'm missing 50 from 2021. I'll do that later in the year, I guess. Damn, so I'm not going to be a 500 star holder by the end of this month. Unless I quickly do 2021 in the next week. That's not going to happen. Yeah, I was going to save 2021 for something to do halfway through the year. That way I can spread it out a bit. Um, but yeah, have you done past many of the past years? What about you, Amaro? Have you gone back and done some of these? I can actually check. Let's check if Amaro is keeping up. You haven't done 2015. Um, all right, so actually this year is my first proper one. Yeah, it's becoming more and more popular every year, definitely. It's a shame that the global leaderboard is no longer worth anything because people are using AI to solve it. But private leaderboards is still a thing, and for a lot of people, private leaderboards was the way to go anyway because time zones kind of make the leaderboard a little unfair, especially for like Europeans who would have to wait. No, well, it starts at like midnight in the US, doesn't it? Because that's the only time Eric really has a chance to be there at his computer because he has like a family and a job and everything. So the best time for him to actually be there at his computer, ready to handle any issues, any site outages or anything, is midnight. So that's already not a great time for Americans. If a problem takes like multiple hours. Oh, wrong event. Going back to 2024. Have public leaderboards ever been void of cheating for anything? Well, before AI, pretty much. Like, there wasn't really a way to cheat. There wasn't a rule against... Before AI, there wasn't really anything that was against the rules. You were allowed to use any tools. The only thing you weren't allowed to do was copy other people's answers. But it wasn't easy to do that anyway, and I can't see why anyone would bother. Because you get a different data set to them. It's the only way you could really cheat is to collect so many data sets from different accounts and different people and know the answers for those data sets. And I hope you get one that matches yours. So I don't think anyone would have ever done that, because why would they? It's like, it's more work than just solving the problem. And Eric also asks that people don't post the data sets, the input data on GitHub or anything, and most people have respect for that. So there's not enough data out there for anyone to even cheat from. So yeah, I would say before 2-3 years ago, the leaderboards were void of cheating because there just was really no motivation to cheat or any real way you could cheat. Like, if you noticed something was like a famous mathematical sequence and you Googled the answer, that's perfectly fine. That was a legitimate way to solve the problem, and that was allowed. In fact, the first year that AI was used, it was allowed because there was no rule against it. And I believe that the conclusion that Eric came to was like, okay, it's a tool, people are using it. It was never against the rules because it never existed. At least no one had ever come up with a tool that could do this. So that year it was actually allowed. And I remember there were like people were posting like blogs, like how they solved it, how they got to the top of the leaderboards with AI. A lot of people are not happy about that, but at the same time, it wasn't against the rules technically. All right, so yep, we're done. I gotta go upload the YouTube video and all that stuff. All right, catch you tomorrow for day 21. There's only 1, 2, 3, 4, only 5 days to go. And Christmas Day will probably be an easy one because it's only part 1, no part 2. You have a YouTube channel? Yeah, I upload all these, I archive these all on my YouTube channel. I mean, I can find the... Oh, here's the link right here. I basically just like archive all my gameplay videos and stuff there, so it's just like a whole mess of stuff. But there's Advent of Code in particular. I'll just paste it here. So yeah, I'll upload the video there. All right, well, is anyone still doing it? Mega Man Advent, the Adventure of Link, Adventure Autist. Oh, that's in German. Idle Adventure. Epiphanes has been doing both satisfactory speedruns and Advent of Coding. That's crazy. But he's on live. Okay. All right. That's it. Thanks for watching. Oh, yeah. See you tomorrow.